I'd like for you to do this next one. Find the point on the curve y equals the square root of x that is the closest to the point 3, 0. Come back when you're done. All right, it may have been a lot to ask you to do this all on your own for the second example, but let's see how you did. I have here the graph of y equals the square root of x, and something I didn't really say before, but I hope is implied. This is single variable calculus. I have here x2 and x1 and y2 and y1, and I want everything in terms only of one variable. If you want multiple variables, take third semester calculus. Now, so for xy, because x is equal to the, y is equal to the square root of x, xy is equal to x comma square root of x. So there's my curve, and then I have the point 3, 0. And there are various distances between the point and the curve, but I'm looking for the shortest such distance. I know the distance formula is the d equals the square root of x squared minus x1, the quantity squared, plus y2 minus y1, the quantity squared. I will be squaring that, and so I'm finding the minimum of the square of the distance. And then I've identified x square root of x as x2, y2, and then 3, 0 as x1, y1. And with that, I have that uppercase D is equal to x minus 3, the quantity squared, plus the square root of x minus 0, that quantity squared. The bottom line after I simplify and differentiate is that x is equal to 5 halves. Since y is equal to the square root of x, y is equal to the square root of 5 halves. And so the closest point is 5 halves, square root of 5 halves. And yes, square root of 5 halves is perfectly acceptable as a form of an answer. You don't need to rationalize denominators. Now let's talk about this square of the distance versus the distance itself. Because uppercase d is lowercase d squared, we know that if I were using lowercase d, we would have, so I'll just consider. We're done with the problem. I'm just moving on, or I'm going to continue to talk. Lowercase d would be the square root of x squared minus 5x plus 9. And if I were to differentiate that, I would have d prime is equal to 1 over 2 times the radical of x squared minus 5x plus 9 times the derivative of the inside function. We're going to use the chain rule. Well, the derivative of the inside function is 2x minus 5. The only thing that can make a fraction equal to 0 is if its numerator is equal to 0, and that's what I did here. So you can see that the math actually is really the same in finding a critical number, whether I'm using the square of a distance or the distance itself. It's just the calculus is easier with the square of a distance. Now we have a volume situation. Consider the following problem. A box with an open top, no lid, is to be constructed from a square piece of cardboard 3 feet wide by cutting out a square from each of 4 corners and bending up the sides. We want the largest volume for such a box. Let's make sure that we have the correct visual for this. So I'm going to draw a square, and this square is 3 feet wide. So 3 feet here and 3 feet in the other direction. And then we're going to cut a square out of each corner. All right, so here's the square piece of cardboard. We've cut out the corners, and then we're going to fold up the sides. Now, depending on the size of the corners, squares that we cut out in the corners, we could have a box that's really shallow, maybe something that's good for like transporting tomatoes. Or we could have, if we cut out really large squares, we could have something that's really tall, maybe suitable for shipping a poster. Or something that's kind of just bigger. And in each of these cases, the area of the bottom square, these are all squares, is the same as the area of this square. Furthermore, in each of these cases, the height is the same as the length of one side of the square of the corners that we're cutting out. Now I've called them height. I guess I'll leave it as h. Okay. So what is an expression that gives me the length of one side of the square base? 3 feet minus h minus h. So this is 3 minus 2h by 3 minus 2h. So now we can consider the volume as a function of h. Remember, we want only one variable. Well, 3 minus 2h, the quantity squared, times the height, right? Volume is the area of the base times the height. With this in mind, I'd like for you to answer the question. Rather than using the product rule and the chain rule, I went ahead and multiplied out our volume function. So I have 4h cubed minus 12h squared plus 9h. Differentiating and setting equal to 0 is going to give me that h equals 3/2 or 1/2. How do I have two answers? We didn't do this in either of the previous examples, but it would be a good idea, generally speaking, to verify that what you have is actually a maximum or a minimum, depending on what you're looking for, right? And the quickest way for us to do that in this case would be to use the second derivative test. So v double prime of h is equal to 24h minus 24. I can see that the second derivative is positive for h equals 3/2, and the second derivative is negative for h equals 1/2. Positive is going to be concave up for the second derivative, right? Second derivative being negative is concave down. Concave down is associated with a local maximum. We could also reason that we can reject 3/2. Look, if I have a box that or a cardboard square that has a length of 3 feet on a side, if I cut out 1.5 feet, then what I've done is I've taken this cardboard square and I've turned it into 4 cardboard squares. I'm not going to have a box. In fact, the volume associated with that you can find is going to be 0. Now, we were not asked for h equals 1/2. We were asked for the largest volume that a box can have. We have this expression that gives us the volume. So if v of h is equal to 3 minus 2h, the quantity squared, times h, then v of 1/2 is equal to 2. So the largest volume is 2 cubic feet.